The section also rectangular. So take note of this rectangular section. Height to width ratio, they have given the ratio. Right? Once you get the one dimension, you can adapt this ratio to find out the other dimension. Ratio also you have to maintain. These are the conditions given to you. According to this design, they should maintain this ratio. Also, the beam rests on smooth supports, just sitting on the supports. These are the conditions given. Let's draw the strategy is to draw the free body diagram, write all the formula. Am I right? The strategy means you must strategize first. What are the methods you will adapt? What are the concepts you will apply? What are the given data, free body diagram? Let's start with the free body diagram.
Teacher, can I see the question again? The last part?
Question you didn't complete yet.
The last one, the last little part. Just. Thank you.
All of you must write and solve. There will be short question on this chapter. One of the CO you have to achieve. I will ask anyone randomly to show your answer on the screen. Please be ready. Don't cheat me. Don't try to cheat yourself. It's very simple, direct. I'm here to guide you all through. Right, done? Okay. Or you just take snapshot and keep it with you. Simple analogy, you already know how to do bending moment and shape of diagram for this condition, given loading and support condition. After that, you apply the bending stress equation to find out the unknowns. Okay. I explain this first, then we go to next slide on this, so that is clear for you. All of you should work out. You are not doing yourself. You are working together with me. Then it is not a much. It's not a big deal. Alright. Just understanding is required. I want to see how you reproduce. Okay. That's okay for us. Remember the span, right? 2 meter, 4 meter, and 2 meter. All of you can see the slide. Yeah. The loading is given. Support is given, right? Support is already there. Because of the support, it will have some moments, reactions, right? Right. Start from here. We solve for this is the free body diagram, right? Free body diagram, forces and moments. Start from here. You calculate the loading, right? And then this diagram. So the ratio between depth to breadth ratio is equal to like this. So you match B to D, D to 1.25. So D is 1.25 times, B is 1 time and D is 1.25 times. That's what written here. We make the ratio like this, B, and this is depth. This value is depth. Right here. This is your depth. Okay. Based on the given data, and then you follow by just simplify and keep it here for your IX. Assuming bending moment controls, maximum bending moment is equal to this much. Can you all work out now? First of all, we need to work out the bending moment and shear force, and then only we can substitute in this. Can you all work out the bending moment for this condition? Can you do it? It's not given here. Start from one direction, right? They follow the same method that we explained, right? You can start from here or from here. Work out the bending moment at this point. Do the shear force first, shear force first. Because the free end, right? It's a free end, no reaction. Then it's like a cantilever. And then moving on, you will have the moment. You convert this load into distance, you will have this moment. And then when you come here, convert this load into distance, you will have this moment, followed by this. You are having this seesaw, right? Seesaw with the bridge, with the beam like this, supported here, and a kgs here, some kgs located here. I think he will give the number now, 20 kg I think. When this is pulled, pushed down, the loading, when it is loaded like this, with this distance, you can see the moment, how he is using, just using 2 fingers to move it. Okay, can you hear me? Can you hear distance, right? With this distance given, right, very long and very short between the support, right? And this is the load 20 kg, and the load tends to move like this way. The load we are applying the load moment, or we are applying the load in this direction. This is the first case, right? This is the first case with the longer and shorter in this direction. How he is moving? He is just moving with, you see here how he is moving the object. Put the effort, see the effort, just two fingers he's using to move it. On the other hand, when it goes to the next one, let it go. Still he's talking in Hindi, you cannot understand. Maybe some of you can understand, I suppose. Later I play the, may I give you the link, you go and see the things. But see, another thing is the distance changing. See, the distance last time is longer, but the distance is changing. He has to use both hands to lift the same 20 kg. See here, last time in this first case, he just used two fingers. Here using full hand or both hands to push this way because the distance is changing. This distance is increasing at 20 kg times the gravity, right? So much newtons he has to apply. And coming here, again the distance reduce over this point. Distance reduced for the same kg. You see, cannot move at all. With both hands also he cannot move. Has to push very high loading so that he can move it. That is why the distance is matter in terms of finding the moments. Right? I repeat once again. In the first case, for the same 20 kg, when the distance is changing, automatically the load applied have to be changed. Just very light effort, just two fingers or just light motion with this long distance can go. On the other hand, the distance is very small. At the same time, when the distance is increasing and the other side also distance is reducing, he has to put more effort to move in this case. So now you can understand why the distance matters in terms of moment, right? So you cannot move. The last one even very high because the lever arm is very high. For this case, the lever arm is very high. Last one, the lever arm is very less. Here, the lever arm or the distance at which the loading happening is very high. On the other hand, it is very low. If it is equal, then it is balanced. That's why the equilibrium. If this distance is equal to this, you can apply just 20 kg here to lift it up. Because the distance is less, you have to apply more than 20 kg or the distance should be very high to lift it. Because the distance is very low, it is not equal to this distance and the loading, you have to apply more loading compared to this load because of the short distance to move the same weight. Are you clear? It's very good example for you to work out the bending, shear force. Shear force means the load. How much load is acting on it, am I right? And this value of the load is given as 8 kilonewton meter, am I right? 8 kilonewton meter. Means can you imagine per meter the load acting on it is equal to, then what is the meaning? Per kilonewton, per meter square cross section. If you cut this section, if you cut the section here, it will look like a rectangular one. Okay, rectangular beam. All right, just like this. If you project it, it will be having like this. Rectangular beam, rectangular beam. Located like this, okay? Rectangular beam, if you project it, this is the support is somewhere here, right? And you will have loading on top, right? Loading on top like this. At the cut section will show a clear rectangle, right? And clear rectangle ratio also given to you. The ratio is such a way that height to depth, let it be depth. Depth to width ratio is 1.25. Depth to width ratio is 1.25. Means what? Have a height to width ratio of 1.25. According to the calculation here also, it is showing breadth is taken as breadth or width, and then depth is higher than the breadth. Okay, if you take this as breadth B, depth is 1.2 times the depth, the breadth. Okay, which is equal to D or D. This is D, depth of the beam. cross section will be rectangular, and the load is like this. It might be a beam located at the bridge or culvert or anything. Okay. Now let's solve this question with it's a free n. If I put like this, it's not showing a free n. I just put it right. In this case, you have, if it is a straight line, just UDL is acting, right? UDL is acting and the supports are at the n. Normally what you do, you convert into span, right? If this span is like L meter, automatically you convert this into point load by multiplying. If this is W Newton per meter, and this is L meter, what you do, you can convert this into point load by multiplying W times L, right? When you do W times L, automatically Newtons coming in, means point load. You can write here conveniently as W L Newton is acting. Clear? W L Newton is acting at this point. Alright? This is what I am doing here, right? This is what I am doing here. W times L Newton is acting at this point. We have to do change into point load so that you can calculate all the values. But in our case, there is a support in between, right? Not at the end. So same thing we are doing here. The load started from here until this point. So let's calculate in between. I'm only calculating the load. If it is a point load, you don't have to multiply, right? Because per meter run is given. Meter run is how much? 8 kilonewton per meter. Because per meter run is given, you have to draw the value. You have to, this is the axis and this is my axis. Actually, you have to put it as a dash. Because a graphic, it is my axis only. From the axis I'm going to draw. It is 0. Moving on, there is some loading. So you have to give some value here. How much is the value? This is written by, let's move by node by node. Next node is this one. My next node is this one. How much is this? Or let it be RB. You can even calculate it. RB, or what is the value here? RA, let it be RA. Usual method, RA and RB. Okay, RA and RB. So when you calculate from here, use this area to calculate from A. This is A. I do in this direction and this direction. X-axis, one dimension. So what I have, start from here. To find RA, you resolve between this and this. So RA is equal to 8 times 2, which is equal to 16. I put it as negative. Okay, put it as negative because it's downward. So I will mark the value as 16 here. Okay, I mark the value as 16 here. Okay, value of RA will be 16 minus 16. So I have to give some value which is downward. 16 minus 16 I have given, right? Minus 16 because RA only. I didn't account for load yet. I only accounted for this value. 16, how much is the value? Kilonewton. This is in kilonewton per meter. This is in meter. Then you end up with kilonewton shear force. And then I cannot stop here because there is another loading going on, right? Still loading is there. Including this point, there is a loading. How much is the loading? That is equal to 16 again, right? Again convert it. If you convert it from here to here is RB. I don't put, I just put the value only. From here to here is 8 times 4 meter. 8 times 4 is 32, right? So there is something like 32 existing in this area, right? 8 times and the 4, 32 is here. So you have to mark 32, add with this value. With this value, we are working from left to right, left to right. I write better right on left to right. When you do, with this value minus 16 kilonewton, you need to add the 32 value, 32 for this span. So I end up with positive 16. So this is going to be reducing to positive 16 at this point. Positive 16. Positive 16 kilonewton, and then join this one because there is a reaction, right? RB, let it be RB. There is a reaction at this point. So once I reach positive 16, 32. Actually, this is 32 at this point. Better write down 32 at this point. Okay, at this point. But cut minus 16 will be my positive 16. Okay, positive 16. Then moving on here, again 32 here, right? 32 downward because it's acting downward. Minus 13 plus 16, you will end up with minus 16 here, right? So that is why the value is going down to must reach here. You cannot continue the straight line, reduce because the load is acting downward. When the support is trying to, you see here in the diagram, when the support is trying to resist, when the support is trying to resist the load coming in, there is another load pushing it down. Hence you will have downward, net result is downward. Again at this point you will not have just 16, load continues. If no load, then you stop here. Because the load continues, you will have another 16 here, right? Another 16 or 32. You will end up with 32 here. You will have 32 here, continue, carry on here. You will have 32 minus 16 because it's already minus 16, right? Minus 16 minus 32 plus 36 will be minus 16. So you have minus 16, you end up with positive 16 here. Moving on, you have load, otherwise I stop here. Still you have load, right? You calculate how much is the load at this point, times 2, right? 8 times 2, 16. So downward, 16 downward. So you will have 16 positive already, minus 16 here. At this point is minus 16 equal to 0. So you need to reach 0. Clear? I repeat if you want at this point. Let me draw first. 0. How I achieved 0 here? Already 16 here, but there is a load here, right? Between the support and the end, there is a load. So much load is acting on it. So I will have 16 already the original value minus downward load, which is 16 equal to 0. So I reach the value 0 here. This is how you plot the diagram for shear force values. Graphically, the shear force values are plotted: minus, negative, minus, positive, and then this is minus and positive, end up with 0. If the load is continuing, you have to repeat based on the loading, other types of loading. If it may be point load or UDL. Okay, let's move on to the bending moment diagram. Bending moment also you can calculate and see. Enter. Cannot insert slide, huh? New slide. Okay, clear. Same diagram you take it, copy. Okay. Pasting and duplicate is easy. Now it is okay. I just drew from here. Draw the line again. We are going to do the bending moment diagram. Okay. Bending moment diagram. Start from again left to right, but now you have to consider the distance. In addition to loading, you have to consider distance because bending moment is force into distance, right? The lever arm is important. To apply this formula, you are starting from here. Write down the reactions. Better write down the reactions, otherwise you will not get the answer properly. This is 2 meter, right? This is 2 meter, and this is 4 meter, and this is 2 meter, and you have a reaction RA is equal to 16, RAB is equal to 16. Mark these loadings and all. And then another loading like this, 8 kilonewton per meter. These are the loading and the reactions. You need to write down the loading and reactions so that you can calculate the exact value of your bending moment. Start drawing the bending moment diagram. I do it in another, okay, just use the same color, same marking. And because free end, right? Free end, you still have the 0 value here, right? At this point is 0 value. No force, no moment, right? Because when this force is become 0, when force becomes 0, equal to whatever the distance you have, the distance also 0, so we end up with 0 value at this end. But you have a load and distance, right? As you move on, you pick up the distance. When you pick up the distance, automatically you have a moment because of the loading, isn't it? Not only moment because of the loading, because of the self-weight of the body itself, there will be moment from this point to A. So how do you calculate this one? by distance, right? Loading is 8 kilonewton per meter. I write here, but I remove this cut this one. Where is my calculator? Okay, somewhere here, right? Start from here. At this point is 2 meter distance. Loading is 8, right? The same value you can take it, 8 kilonewton per meter. So my moment at RB, I mean at this point will be between, let it be O to A will be 2 times A, which is 16. Whether clockwise or anti-clockwise, just keep the clock here. I am taking about this point, right? 3, 1, 12, 3, 6 and 9 here, right? The clockwise or anti-clockwise, positive or negative? Due to this loading between O and A, you take this as A and this as O. Between O and A, I keep the clock, and about this point I am taking, so it will be clockwise or anti-clockwise. Okay, somewhere here, somewhere here, right? Somewhere here. And because usually you have to straight line, I mean an inclined line, okay? Because it's usually you have to put an inclined line. So this much value is there, right? This much value, 16 kilonewton meter is there. And moving on, you have another reaction, right? Another reaction at this point. How much is the reaction? 16. It is reaching 16. But RB is already having negative 16, right? Negative 16. So the net will be acting at, this is at A, at A I am writing, this is at point A. So because of this loading between O and A, you have a load of moment of 16. And then at 16 already reaction is there. It is reacted by the RA. So I will end up with 0 at this point. So it is reaching 0 here. Okay, value 0. I don't put 0 here because already having O. Right. After this, moving on, when it will be, D is 0, 0. So just focus this point, is 0 also. And then, and this point also 0, right? And this point also 0, right? Okay. Start calculating. Load, this much load, this much load into distance, you will have 16. And when you come here, there is another 16. Just mark here the value of 16 here, 16. And then when you cross this value, it will be minus 16 plus 16 will be 0. And then moving on, another 16 is here. It's become positive 16. But when it comes here, negative 16, you end up with 0 at this point. Okay, this is the diagram for bending moment. I repeat once again. Started here 0, loading is 8 times 2 16, so positive 16, right? Acting downward, that's why I mark the value of 16 here. But there is another reaction already here, right? There is already a reaction. Negative plus negative is 32, right? Negative plus negative is 32. So you will increase the value, or it will get cancel each other, because this reaction is supported by this load. So you end up with 0 here. And then moving on another load, there is no support in between. So increase the load to 16. At load again, at this point again, it is cancelling with the reaction produced here. Moving on, there is some load, keep increasing to 0. So you can calculate the value like this for the given UDL and end up with the bending moment value of, let me take the value maximum bending moment. Maximum bending moment equal to 16 kilonewton meter. Maximum value of maximum bending moment produced by this loading is 16 kilonewton meter. Both positive values. Okay, let's calculate the value. Just substitute the value of bending moment here. Use this equation from bending stress equation, which is sigma allowable is equal to my by I. Let it be y. Lever arm I will explain now. And then if you substitute the value of allowable that is given to you already, and 16 is your moment, kilonewtons changed to newtons, and then the lever arm, right? Lever arm is, just take the rectangular value. How much is the depth? The depth is point, that's not right in the question, it is given, right? 1.25 times the The ratio of the height to depth is the depth is 1.2 times the width. Okay, write down here. 1.2 times 25 times, 1.25 times 1.25 1.25 times the width. Okay. Okay. 1.25 divided by 2 will be 0.625. So middle portion, I take middle portion, which is the centroid, which is centroid. The centroidal distance between the maximum is occurring at the top layer, right? It may be occurring at the top layer, bending stress. So when I take this y, this as y bar or y, the value will be half of this one. So that's why I'm taking 6.25. The full is B, right? B. So I take 0.625 as a B, I mean leave it on, divided by I we already calculated in terms of the ratio given, right? We take this value, substitute the I, you have end up with the unknown B is equal to this much. Is this clear? And then you have the ratio already, right? Your H is equal to 1.25 times. Just use the same ratio, you can find the unknown, other unknown. H is equal to 1.25 times B, which is equal to which is equal to 264. And then next slide, you're following. We found the one dimension, which is H, depth of the depth and width of the section are found out. That is also the question, right? Find out the dimensions of this. Listen, find out the dimensions of this when the ratio is maintained like this. Final answer will be, we found the dimensions like this. The width of the member is given as 211 mm, and the depth is for given condition of loading by finding shear force, bending one and the section. Any question? I stop here. Any question in the calculation of bending moment?